So in this video, I want to talk about the partial differential equation, or a partial differential equation called the heat equation, which can be solved using much of the technology that we've been discussing. In particular, we can approach it using the idea of Fourier series. So that's what I want to talk about here. So the heat equation has to do with, it's an equation which governs the dynamics of heat in a material. So you might imagine you have a heat conducting material like a metal bar or something like that. And for us, this bar is going to be one dimension in space. Okay. There are versions of the heat equation for higher dimensions. All right. But we have something like this, and we'll set up a coordinate system in which this side here is x equal to 0, and this side over here is x equal to L. Okay, so we'll track positions along this bar using x. And what we're interested in understanding is this quantity u of x comma t. So this is a function of two variables, x and t. X will represent position along the bar, t will represent time. So u of x of t will be the temperature in the bar at position x and time t. Okay. And there's going to be a partial differential equation which governs the dynamics of this, which is we call the heat equation. And that partial differential equation we can write down. It's given by the following. It's alpha of u sub xx is equal to u sub t. Remember, when we write these subscripts here, what we mean are partial derivatives. So u sub xx is the second partial of u with respect to x twice. And u sub t is the partial derivative of u with respect to t. Alpha here, crucially, is just some constant that has something to do with the conductivity of the heat through the bar. So alpha we're going to treat as a constant. This is called the heat equation. It's a partial differential equation. But it's special because it's a linear partial differential equation. And the impact of that is that if we have two different solutions to the heat equation, then we can take any superposition of those two solutions and again get a solution to the heat equation. Okay, that's what linearity means in this context, and it's going to be very crucial for us in our Fourier series approach to solving it. Now, we should specify some further assumptions that we want to make in order to make this problem solvable. We're going to specify, for example, what are called boundary conditions. These are specifications of what's going on the boundary of the bar. So we'll specify that u of x, well, when x is 0, so u of 0 comma t is going to be equal to 0. So you might imagine that that left hand of that bar is its temperature is being maintained at 0 degrees. Okay, and similarly, we'll do the same thing on the other side. That u of L comma t is equal to 0. The temperature at x equal to L is also going to be 0. You might imagine maybe they're sitting in like an ice bath or something like that, and the temperature is again maintained at 0 degrees on either side. Okay, these are called boundary conditions. Boundary conditions. Okay, and then we're going to have an initial condition for the bar. So the initial condition for the bar is going to be what's going on with the temperature distribution at time t equal to 0. And we'll just call that f of x, and we'll keep f of x unspecified at this moment. Okay. This is the sort of setup that we want to approach. And again, we're going to call this the initial condition of the bar. This is the data that we are going to try. This is the data that we're going to be given, and we're going to try to solve this heat equation using all of this information, and hence learn about the dynamics of the distribution of heat within this bar. Okay, so how are we going to do this? So we're going to make a crucial assumption. Which is that of separability. we're going to assume that u of x comma t. Oh, I feel stupid even writing this. Let me do this differently. This is going to be that u of x comma t can be factored into a product of a function of x only and a function of t only. And we're going to call those functions of x and t capital X and capital T, just following the conventions that are in the textbook. Okay. Hopefully you can follow along without too much difficulty. Now, please understand that this is an additional assumption that we're going to bring to bear into this problem. Not all functions u of x comma t satisfy this kind of separability criterion, where we can separate out the bits involving x from the bits involving t. Some functions do. Not all functions do, however. Okay? But we are going to find solutions, hopefully, under this critical assumption. All right? Now, under this critical assumption, what are some implications of it? Well, what happens if we plug this u into our heat equation? So looking at this heat equation here, and let me just box this information over here because this is really important data. If we take the second derivative of u with respect to x, then what we obtain is, because we got this factorization of u in terms of as x times t, and x depends only on x, small x, and t depends only on small t. The second derivative with respect to x is going to be x double prime of x. So notice, I'll just write it like this. Notice that u sub xx in this, under this assumption, is equal to x double prime of x times t of t. Remember, the bits that involve small t are considered constant when we take the derivative with respect to x twice. And similarly, u sub t is going to be x of x times t prime of t. We can sort of treat the bits involving x as constants, right? Great. So we plug all of this into our heat equation. All this data goes into the heat equation, and what we learn is that alpha times x double prime of x times t of t is equal to x of x times t prime of t. Okay? Very straightforward so far. Hopefully all of this is understandable. Now what I'm going to do is, and this is where the separability assumption is so useful, I'm going to segregate everything that involves x on one side of the equal sign and everything that involves t on the other side. So what this is going to lead to is the following equation. This is going to lead to, and I'll write this in red because this is interesting, x double prime of x divided by, wait, do I mean it? I do. X of x. This is equal to t prime of t divided by alpha times t of t. Okay? Now, here is where we have to really think. We have to really think. Because the thing that I want you to notice is that this side involves x only, depends only on x. It does not in particular depend on small t at all. This side is time invariant, okay? Whereas this side only depends on time. It is space invariant, okay? So if there is any variation in either time or space for either one of these quantities, which are supposed to be equal to one another, okay? If there was some position dependency, let's say, on this side, some actual position dependency, then that wouldn't be reflected on this side. Does that make sense? And similarly, if there was time dependency, if there was actual change in the value of this quantity as t changed, that change would not be reflected on this side because of the fact that this is time independent. So what conclusion do we draw? we draw the conclusion that this quantity here cannot really be time dependent, and this side here cannot really be position dependent. They both therefore must be constants, and they're equal to the same constant. That constant we're going to call negative lambda. These must be constants, must both be equal to a constant. And we're going to call that constant negative lambda. I'm allowed to do whatever I call the constant whatever I want, but for good bookkeeping practices, I'm just going to call it negative lambda for reasons that you'll see. Okay? So that gives rise to two equations. The first equation is that x double prime of x over x of x is equal to negative lambda. Okay? Now I'm going to multiply both sides by big X, so I get that x double prime is equal to negative lambda times x, and then I'm going to add lambda x to both sides. That's my first equation. So this is equivalent to that, and this is, of course, equivalent to that. What have I done? Let me move things over a little bit. Let's move it like this, and then put, and let me make this purple. This is equivalent to that, and this is equivalent to that. Okay? We'll talk about boundary conditions on this equation in just a moment. Let me do the other one for next. And the other one is going to be t prime of t over alpha t of t is equal to the same negative lambda. I'm going to again suppress the of t bit, and what we learn is that t prime of is equal to negative lambda times alpha times t. All right, and then I add to both sides, and what I learn is that t prime plus lambda alpha t is equal to 0. So I have this pair of equations now, these two equations here. Okay? And if I can figure out solutions to that first equation and that second equation, which happens simultaneously, okay, then I can multiply them together using the crucial assumption, and that will give me solutions for you. All right, great. Now, we have to think about also the boundary conditions, for example, and the initial conditions. We have to incorporate them somehow into this system, because I'm saying I want to be able to solve this heat equation by solving these this pair of equations here. But if I'm going to incorporate the boundary conditions and the initial conditions in some way, then I better be smart about that. Okay, let's start with the boundary conditions, because this is what's going to really that we're really going to lean into that part of it. So if we think about x double prime plus lambda x equals 0, let me write that part down here. So let's do x double prime plus lambda x equal to 0. Let's think about what these boundary conditions, that the left-hand side of the bar is 0 degrees always, and that the right-hand side of the bar is 0 degrees always. What are those things saying about this big X? Well, it's saying that big X at 0 is always 0, and the big X at L is also always 0. Those are our boundary conditions. So we have this differential equation. It's a second order homogeneous linear differential equation with constant coefficients. Is very much in our wheelhouse. But we also have these boundary conditions, namely that x of 0 is equal to 0 and x of L is also equal to 0. Right? Both ends are in ice. Cool. Now this is what we've encountered this. This is called an eigenvalue problem. And we are interested in detecting those values of lambda which give rise to non-zero solutions to this differential equation. satisfying the boundary conditions, of course. Non-zero solutions to what's called the boundary value problem. That's the differential equation together with the boundary conditions. And the fact is, and you can check this yourself, that the solutions to this, I'm just shoving this down your throat, the solutions to this are given by lambda given by n squared pi squared over L squared. And I'm going to call this lambda sub n, okay, to represent the nth eigenvalue. And the corresponding eigenfunction we're going to call x sub n. These are functions of x, and these end up being given by sine n pi over L times x. You can check this yourself. This, just go back and study, review how to solve the eigenvalue problem. Okay. Great. This is very important. Okay, so we've solved the first equation, this equation here, and we've incorporated the boundary values into our consideration. What is the solution for this one here? Well, this one, it turns out is very easy. We go back all the way to the beginning of the semester, because what this equation is saying is that the rate of change in big T is proportional to T. That should ping some ideas of thinking about equations like y prime equals ky, right? Going all the way back to the first weeks of the semester. This represented either exponential growth or exponential decay, depending on the sign of k. But in particular, the solution to this would be something like e to the k t, right? So if we think about what the solution is to looking at the second equation here, if we look at t prime plus lambda alpha t. Now remember, lambda is now prescribed. There's only a discrete set of values that lambda can take. Lambda can only be something like n squared pi squared over L squared, where n is an integer, please. N is like 1, 2, 3, 4, 5, etc. A positive integer, all right? So if we plug in that lambda n here, then we're talking about the equation t prime plus n squared pi squared over L times alpha L squared times alpha times t equals 0. Now move this second term over to the other side. Get negative n squared pi squared over L squared times alpha times t. Okay, let me box this because I'm going to refer back to it later. All right. Okay, and let me make, because I don't know, I'm feeling aesthetically challenged by all of what I've written here. So let me change the color on all this style. Make it green. All right, I'm happier now. Now, how do we solve this equation here? When I say this equation, I mean this equation. How do we solve that? Well, we use the y prime equals ky idea, where y is being played by big T and k is being played by negative n squared pi squared over L squared times alpha. Okay, so that our solution is going to be written as t sub n of x, of t. It's going to be the exponential of negative n squared pi squared over L squared times alpha times t. Okay, that's good stuff right there. And now this, we can write down a solution. All right. Now, crucially, okay, if you think about what's going on when t, small t, is equal to 0. Well, actually, let me back up. Let's write down then what I'm going to call u sub n, which is the product of x sub n and t sub n. So u sub n of x comma t, now this is, by this, is going to be x sub n times t sub n. And that's just this exponential times alpha times t times this sine of n pi over L times x. Yes? And what I'm claiming is that that's a solution to the heat equation. Now, is it a solution to this problem in this red box? Not quite. And the reason is, even though it satisfies the heat equation, it satisfies the boundary conditions, because if you plug x equal to 0 in, you're going to get, or x equal to L, you're going to get, think about where that goes. It's going to be in this term. If x is 0 or if x is L, then we're talking about sine of 0 or sine of n pi. And what we know is that sine of 0 and the sine of n pi, 0. So this really does satisfy the boundary conditions. How lovely. However, what isn't satisfied by this equation is the initial condition. Okay? That's a problem. The initial condition is f of x. I don't see f of x anywhere in here. Do you see what I'm saying? So that's a problem. What is the initial condition? So here's what I want to say. This equation solves a different heat problem. This u sub n solves the following problem. It solves u sub, same differential equation, u sub xx is equal to u sub t. That's the heat equation. Same boundary conditions. U sub 0 comma t is equal to u sub, let me make it small, u sub L comma t is equal to 0. Same boundary conditions as before. But what's the initial condition for this u sub n? This is going to be u sub x comma 0. Now, I mean, we don't need to ask. We can just plug in t equal to 0 and see. If we plug in t equal to 0 into this expression here, where t goes is right here, and we're talking about the exponential of 0. E to the 0 is 1. So we're left with just this piece here, sine of n pi over L times x. That's the initial condition of heat in the bar. Okay? But what I want to say is that we have gone quite a long way now to solving this heat equation for general initial conditions. Okay? We just have to somehow use this data, as a sort of building block to build out the full story. So that's what we're going to do in the next one. In the next video, what I'm going to do is solve this by taking my f of x, this f of x here, okay, taking that f of x and writing it in terms of sine n pi over L times x's. And you're going to see how we can then use that. Of course, what it is a Fourier series. We can use that to write down the solution to this problem. Okay? All right, see you in the next one.